Massive stone circles and carved patterns predate written history by thousands of years. These are not random scratches, but the forgotten blueprints of a lost mathematical science. This evidence reveals that advanced mathematics existed long before the first written word, fundamentally rewriting the story of human intelligence. By the end of this journey, you will see our ancient past not as a primitive darkness, but as an age of sophisticated genius. We will uncover how prehistoric builders encoded complex geometry into temples and tracked celestial cycles with impossible precision. What does a mysterious 12,000-year-old pillar tell us about the human mind? How could a society without numbers master the golden ratio? You are about to discover the mathematical secrets hidden in plain sight for millennia. What does true intelligence look like when it leaves no written record? Humanity's mathematical journey did not begin with pen and paper. It was born from the mind's innate ability to recognize patterns in the world. Long before the first clay tablet was inscribed, our ancestors were already thinking in numbers and shapes. They possessed a sophisticated cognitive toolkit, one built not on written formulas but on lived experience. Their world was a classroom of endless cycles and natural symmetries, and they were its most attentive students. Think of a hunter tracking prey, reading subtle signs in broken twigs and displaced earth. This is spatial reasoning in action. Or consider a gatherer who knows exactly when the river will run high based on the moon's phase. This is pattern recognition, a fundamental mathematical skill. These early people developed counting systems using their own bodies, tallying with fingers, toes, and even joints, creating a portable, living calculator. They watched the sky with profound dedication, seeing not just random stars but a grand, predictable clockwork. They observed how the sun's path shifted with the seasons, marking the solstices and equinoxes with nothing more than a carefully placed stone. From this deep, observational knowledge emerged the first concepts of measurement and geometry. The need to divide a space, to create a circle, to align a structure with a star. These were the practical problems that demanded abstract solutions. This cognitive landscape, rich with intuitive understanding, is the true foundation of mathematics. It is the fertile ground from which the astonishing structures we are about to explore would eventually grow. This cognitive toolkit of pattern and proportion found its ultimate expression in stone. On a windswept hill in what is now Turkey stands Göbekli Tepe, a temple complex so ancient it predates Stonehenge by a staggering 6,000 years. Built nearly 12,000 years ago by hunter-gatherers, its very existence shatters the conventional narrative of human progress. Here, we find our first concrete evidence of advanced mathematics encoded in architecture. The site is composed of multiple circular enclosures, each defined by massive, T-shaped limestone pillars weighing many tons. These are not haphazardly placed monoliths. The arrangement is a masterpiece of geometric planning. Researchers analyzing the layout made a startling discovery. The central pillars and the surrounding stone walls form perfect equilateral triangles and near-flawless circles. To achieve this, the builders required a sophisticated understanding of spatial relationships and symmetry. They had to conceive of these shapes abstractly in their minds, then transfer that perfect mental blueprint onto the uneven, rocky ground. This is not simple intuition. This is applied geometry. The precision of these forms reveals a conscious use of proportion and measurement, techniques we once believed were invented much later by settled agricultural societies. How did they do it without writing, without formal numbers? They likely used a simple yet brilliant tool, a rope. By anchoring a central point and using a cord of a fixed length, they could inscribe a perfect circle on the earth. By using that same rope to measure equal distances between points, they could outline an equilateral triangle. This practical technology allowed them to manifest complex geometric ideals into physical reality. The carvings on the pillars themselves, intricate animals and mysterious symbols, may be more than just art. They could be a visual language, a way of recording knowledge and myth, further demonstrating a capacity for abstract thought that directly complements their mathematical skill. Göbekli Tepe stands as a silent, monumental testament. It proves that the human mind was already architecting with advanced mathematical concepts at a time we once wrote off as primitive. The principles first seen at Göbekli Tepe did not vanish. They were carried across millennia and continents, finding perhaps their most famous expression on the windswept Solsbury plain. Stonehenge, that iconic ring of standing stones, is far more than a primitive calendar. It is a colossal exercise in megalithic mathematics. Modern analysis of its ground plan has uncovered a stunning secret hidden in the arrangement of its stones. The positions of the key markers form perfect right-angled triangles, using specific whole number ratios for their sides. These are what we now call Pythagorean triples, the very same mathematical principle that defines the relationship between the sides of a right triangle. The builders used these triples to ensure perfect geometric harmony in their design, a full 2,000 years before the Greek philosopher Pythagoras was even born. This geometry extends into the very proportions of the circle. The arrangement of the stones follows complex patterns that seem to incorporate the golden ratio and sequences of numbers found in nature, like the Fibonacci sequence. These are not random placements. They represent a deep, intuitive grasp of proportion and harmony, translating abstract mathematical beauty into a physical, sacred space. But the mathematics of Stonehenge reached for the heavens as well. Its alignments are exquisitely precise. On the summer solstice, the sun rises directly over the heel stone, casting its light into the heart of the circle. Other stones align with the extreme rising and setting points of the moon in its complex, 18.6-year cycle. To track this, the builders needed more than just patient observation. They required a sophisticated calendrical system, a form of long-term mathematical prediction that allowed them to plan for celestial events that would not complete for a generation. All of this abstract knowledge was useless without the engineering mathematics to make it real. Consider the transportation of the massive sarsen stones, some weighing over 25 tons, from quarries over 20 miles away. Moving them required a profound understanding of physics, leverage, and force. Then came the placement, the famous trilithons, the two vertical stones with one horizontal lintel across the top, are architectural marvels. The lintels are connected using sophisticated woodworking joints, mortise and tenon, carved directly into the stone. The upright stones were even subtly shaped, wider at the top than the bottom, creating a visual trick that makes the entire structure appear perfectly straight and towering. This required a masterful understanding of weight distribution, structural stability, and optical illusion. The builders of Stonehenge were not just astronomers and geometers. They were civil engineers working with a mathematical toolkit we are only now beginning to fully comprehend. Across the sea, another monument whispers of this ancient mathematical tradition. In the green hills of Ireland, the great passage tomb of Newgrange rises from the landscape, a massive, rounded mound older than the pyramids of Giza. Built around 5,200 years ago, its most famous feature is a phenomenon of breathtaking precision. Above the entrance, a narrow opening known as a roof box was engineered with impossible accuracy. For just a few minutes at dawn on the winter solstice, as the sun reaches its lowest point in the sky, a narrow beam of sunlight pierces through this special slit. It travels down a long, dark passageway over 60 feet into the heart of the tomb and illuminates the central chamber in a dramatic burst of golden light. This is not a happy accident. This alignment required generations of precise astronomical observation. The builders needed to track the sun's slow, yearly migration, noting its exact rising point on the horizon day after day, year after year. They had to calculate the precise angle and height for the roof box, and then construct the passage at the exact orientation to capture that single, fleeting ray of light. This was a long-term mathematical project, a promise made by one generation that would only be fulfilled by their grandchildren. The mathematics of Newgrange are carved into its very stones. The entrance stone and many others within the complex are covered in intricate, swirling spirals. These are not just decorative patterns. Many of these spirals are logarithmic, a shape where the distance between each curve increases in a constant geometric progression. It is the same pattern you see in a nautilus shell or a swirling galaxy. To reproduce this shape in stone requires an intuitive, yet profound, grasp of growth patterns and ratios. This is a visual representation of a complex mathematical sequence, etched into rock millennia before it would be formally defined in a textbook. Even the structure itself is a mathematical marvel. The chamber is capped by a corbelled roof, where layers of flat stone are stacked in ever-decreasing circles, each layer cantilevering slightly inward until they meet at the top. This creates a perfectly stable, waterproof vault that has stood for over 5,000 years. This construction demonstrates a masterful, practical understanding of load distribution and structural physics. The builders knew exactly how to offset the immense weight of the mound above, calculating the angles and overlaps needed to prevent collapse. The entire complex is a single, unified mathematical statement, oriented to celestial coordinates and built with geometric principles we would not see again for thousands of years. Yet the mathematical impulse to shape the landscape did not stop at single monuments. In the quiet countryside of Brittany, France, a different kind of wonder unfolds, one of staggering scale and cryptic order. The Carnac alignments are a forest of stone, a sprawling network of over 3,000 standing stones arranged in long, parallel rows that march across the land for miles. This is not a temple or a tomb, but something far more abstract, a vast mathematical diagram written on the earth itself. Walking among these granite sentinels, you feel the weight of an immense, coordinated project. The stones are not placed randomly. They follow a precise, repeating geometry, a rhythm of space and alignment that reveals a mind obsessed with pattern. Researchers studying the site have detected a hidden code within the spacing. The distances between certain stones or groups of stones encode approximations of fundamental mathematical constants. The ratio of the distances in key formations comes incredibly close to the value of pi, the constant that defines the relationship between a circle's circumference and its diameter. In other formations, the proportions echo the golden ratio, that special number renowned for its appearance in natural forms from sunflowers to spiral shells. To embed these abstract numbers into a physical landscape of this scale implies a conceptual leap of breathtaking sophistication. How could a prehistoric society achieve this? The secret lies in a standardized unit of measurement. Analysis strongly suggests the builders used a common megalithic yard, a precise length they applied consistently across the entire site. This universal measure allowed teams working on different sections, perhaps over generations, to maintain the integrity of the grand design. They were not just placing rocks, they were surveying. They were using ropes and stakes to create a giant grid, a coordinate system that turned the entire terrain into a living canvas for their mathematical ideas. But what was the purpose of this colossal effort? The alignments are not merely terrestrial. Many of the dominant stone rows point directly to significant celestial events, like the rising of the sun or moon at a solstice. This transforms the entire complex into a colossal astronomical observatory, a permanent stone computer designed to track the cycles of time. Imagine the coordination required. Moving thousands of multi-ton stones into perfect lines, all while maintaining precise geometric and astronomical relationships. This was a civil engineering project that would challenge modern planners even with satellites and software. The Carnac stones are a silent testament to a society that thought not in words, but in lines, ratios, and the silent, perpetual motion of the heavens. This same geometric impulse was flourishing on a Mediterranean archipelago. The Maltese islands are home to a collection of prehistoric temples, so architecturally advanced they seem to defy their own age. Built between 3,600 and 2,500 years before the Common Era, these are not simple stone huts. They are complex, cloverleaf-shaped structures of immense scale and staggering precision, and they hold mathematical secrets in their very foundations. The temples like Haga Kim and Mnajdra are masterpieces of geometric design. Their most striking feature is the use of complex elliptical shapes and apses, creating a layout that is far more sophisticated than a simple circle. To design such a form requires a deep, practical understanding of geometry. The builders were working with curves and focal points, planning multi-chambered spaces that flow into one another with a deliberate, harmonic rhythm. This was not random piling of rocks, it was architectural calculus executed in limestone. How did they achieve such consistency across multiple temples built over 1,000 years? The answer lies in a universal standard. Researchers have discovered that every major temple in Malta was built using the same unit of measurement, now called the Maltese foot. This was their megalithic yard, a fixed length used by master builders to ensure that every wall, every doorway, every chamber was in proportion. This standardized measure was the backbone of their entire architectural tradition, a mathematical constant that allowed this sophisticated knowledge to be passed down through generations without a single written word. The precision extends to the sky. The main axes of many temples are meticulously aligned with the rising sun of the solstices and equinoxes. At Mnajdra, the rising sun on the equinoxes illuminates a specific corridor, while the solstice sunbeams strike carefully placed stones. This celestial choreography required the same long-term astronomical observation we saw at Newgrange, but here it is integrated into a far more complex architectural form. The temples are a fusion of earth and sky, geometry and astronomy, all bound together by a system of measurement. The proportions of the spaces themselves reveal an even deeper layer of knowledge. The layouts demonstrate an intuitive grasp of harmonic proportions, the same pleasing ratios that would later be formalized in Greek architecture as sacred geometry. The relationship between the chambers, the width of the passages, the height of the altars, all seem to follow a mathematical order designed to create a specific sensory and spiritual experience. Walking through these temples is like walking through a mathematical equation made physical, a silent symphony of stone and proportion that has endured for over 5,000 years. Far from the megalithic landscapes of the West, a different kind of evidence was being etched into clay. In the villages of the Vinča culture, which flourished across Southeast Europe over 7,000 years ago, we find not towering stones, but small, fired clay artifacts covered in a mysterious code. These are the oldest known symbols of their kind in Europe, a tantalizing glimpse into a mind on the verge of a monumental breakthrough, writing itself. Yet among the swirling lines and animal figures, a more practical story emerges, one written in the universal language of mathematics. Scratched onto pottery and clay tablets are clear, repeating sequences of lines and dots. These are not random decorations, they are tally marks, a straightforward counting system used to record quantities, perhaps of goods, animals, or days. But the Vinča symbols go far beyond simple counting. We see intricate geometric patterns, grids, and what appear to be schematic maps or architectural plans. Most compelling are symbols that look strikingly like early numerals, distinct marks that could represent specific values in a standardized system. This suggests they were not just counting, they were calculating. The evidence points to the use of a common unit of measurement, a consistent length used for trade and construction, found on rulers and measuring sticks across the region. Imagine a merchant using a marked clay token to ensure a fair measure of grain, or a builder consulting a tablet incised with angles and lines to plan a house. This was a society conducting mathematical operations, managing resources, and encoding complex information without a single phonetic word. These enigmatic carvings represent a sophisticated recording system that managed the mathematics of trade, tracked celestial cycles for agriculture, and guided community projects. The sheer complexity of these symbols and their consistency across a vast area for centuries reveals a developed, shared mathematical thinking. This proto-writing system, with its embedded numbers and formulas, predates the rise of Sumerian numerals in Mesopotamia by centuries. It stands as a powerful testament that the human drive to quantify, measure, and record the world is a fundamental force, one that found expression in clay long before it was ever written on a page. The story of this mathematical dawn extends far beyond the European continent, under the vast, starlit skies of prehistoric Africa. In the scorching sands of the Egyptian Sahara, the stones of Nabta Playa tell a silent, profound story of celestial genius. This was not a grand temple complex, but something arguably more brilliant, a compact and brutally efficient stone calendar built by cattle-herding nomads over 7,000 years ago. At first glance, it appears as a simple collection of rocks, but its geometry reveals a mind thinking in lines, angles, and cosmic cycles. The central structure is a small stone circle, not even 10 feet across. Yet from this humble center, lines of stones radiate outward like spokes on a wheel. Other stones stand in isolation, placed with deliberate intent across the flat basin. When archaeologists mapped these positions, a stunning pattern emerged. The alignments of these stones correspond precisely with the rising and setting points of key stars, as they would have appeared on the horizon thousands of years ago. One line marks the summer solstice sunrise, others point toward the stars of Orion's belt and the brightest star in our sky, Sirius. This was a star clock, engineered to predict the coming of the seasonal rains, a matter of life and death for their herds. Creating such a device required more than just watching the sky. It demanded a sophisticated mathematical operation, the translation of time and celestial motion into fixed terrestrial geometry. The builders had to track the slow precession of the stars, note their exact positions year after year, and then codify that moving map into the permanent, unmoving positions of heavy stones. This is applied spherical astronomy, a complex feat of observation and calculation. The geometry of Nabta Playa is equally advanced. The arrangement of the central stones forms clear sightlines that create precise angles. These are not rough approximations. The builders used a consistent unit of measurement, a proto-cubit, to ensure the accuracy of their alignments. They were effectively creating a mathematical grid on the ground, a physical representation of the celestial coordinate system above their heads. This demonstrates a conceptual leap from simply observing a pattern to actively modeling it, a fundamental step in the development of abstract mathematics. The existence of Nabta, Playa, and other African sites fundamentally rewrites a long-held historical narrative. It proves that the drive to quantify the cosmos, to use geometry and measurement to understand time itself, was not a uniquely European or Middle Eastern invention. This was a global human impulse, from the Sahara to the British Isles, from the Maltese Islands to the Nile Basin. Our ancestors were independently arriving at the same profound conclusions. They looked up at the same stars and saw the same patterns, the same mathematical order woven into the fabric of the universe. Their solutions, carved in stone across the world, were different expressions of the same brilliant, innate human intelligence. The silent stones of Scotland hold a geometric secret just as profound as the great circles of the south. From the remote Isle of Lewis, the Callanish stones rise against the sky like a petrified forest, their stark silhouettes telling a story of mathematical genius. This is not a simple ring of standing stones. It is a complex cruciform shape, a central circle with arms extending in a precise cross pattern. To design such a structure required a master plan, a mental blueprint of intersecting lines and curves that demonstrates a sophisticated grasp of spatial relationships. The geometry here is breathtakingly advanced. The layout of the stones incorporates the proportions of the golden ratio, that special number of harmonic beauty found in nature and classical art. Even more strikingly, the arrangement forms perfect Pythagorean triangles, using the same whole number ratios for the sides of right-angled triangles that would later bear the Greek philosopher's name. This is not a coincidence. It is the deliberate application of a mathematical principle to create a sacred and perfectly proportioned space. This geometric precision extends far beyond the earth and into the heavens. The central monolith at Callanish, a towering 15-foot stone, acts as a giant astronomical sighting device. The southern avenue of stones points directly to the setting point of the moon at its most extreme southern standstill, an event that occurs only once every 18.6 years. Other alignments target the rising of the star Capella and the sun's position at the equinox. To achieve these alignments, the builders had to think in 3 dimensions. They were not just drawing lines on the ground, they were projecting lines across the dome of the sky. This required a working knowledge of spherical geometry, understanding how to translate celestial movements into terrestrial sightlines with exact angular measurements. They were effectively creating a permanent stone calculator for predicting the complex dance of the cosmos. What is perhaps most compelling is the consistency found across Scotland. From the Ring of Brodgar in Orkney to smaller circles scattered throughout the Highlands, the same mathematical principles appear again and again. This is not the work of isolated geniuses. It points to a shared knowledge system, a school of thought that spanned the region. The repeated use of specific geometric shapes and astronomical alignments suggests the existence of a master-builder tradition, where complex mathematical and engineering knowledge was passed down orally through generations. They likely used a standardized unit of measurement, a Scottish megalithic yard, to ensure that every circle, regardless of its location, was built to the same exacting proportional standards. These Scottish monuments stand as a final, powerful testament to a forgotten scientific tradition. The builders of Callanish and its sister circles possessed a mathematical toolkit that we once believed was impossible for a society without writing. They manipulated abstract concepts of ratio and angle. They modeled the celestial sphere on the landscape, and they encoded this knowledge into the most durable medium they had, stone. Their silent, granite sentinels challenge our most basic assumptions about the timeline of human discovery, proving that the language of mathematics was spoken fluently long before it was ever written down. But the mathematical mind of our ancestors was not confined to stone alone. They also reshaped the very earth itself, moving mountains of soil with a precision that rivals modern engineering. Across Europe and North America, massive prehistoric earthworks stand as monuments to this forgotten science of soil and slope. In the heart of England, Silbury Hill rises from the landscape, the largest artificial mound in prehistoric Europe. To the untrained eye, it is just a large grassy hill, but to an engineer, it is a mathematical marvel. Its construction required a breathtaking understanding of volume and mass. The builders had to calculate exactly how much chalk and soil was needed to create this colossal form, moving an estimated 12 million cubic feet of material entirely by hand. But the real genius lies in its stability. Silbury Hill has endured for over 4,000 years because its slopes were engineered with the perfect angle of repose. This is the steepest angle at which a loose material like soil can be piled without collapsing. The builders intuitively understood this principle, calculating the precise gradient needed to prevent erosion and structural failure for millennia. They did not just pile dirt, they designed a permanent landform. This mathematical engineering extended far beyond simple mounds. Consider the massive hill forts that crown the British landscape, like Maiden Castle. Their complex, multi-banked ramparts and labyrinthine entrances are not just defensive walls. They are exercises in advanced geometry, designed to create killing zones and channel attackers into vulnerable positions. The angles of the banks, the spacing of the ditches, all were calculated to maximize defensive advantage. This is applied mathematics on a grand, strategic scale. Even more impressive is the hidden infrastructure. Many of these earthworks contain sophisticated drainage systems. The builders engineered channels and conduits to manage water runoff, preventing their massive structures from being washed away or undermined. This required a deep, practical understanding of hydrology, the slope of land, and the properties of different soils. They were not just moving earth, they were managing an entire ecosystem of water and stability. The coordination required for these projects is almost unimaginable. To build Silbury Hill or the Great Hill Forts required a master plan, a mathematical model that accounted for material properties, labor allocation, and long-term environmental factors. This was a society that could visualize a finished project not just as a shape, but as a functioning system, anticipating problems that would not manifest for generations. These are not the works of simple farmers. They are the legacy of civil engineers working with a mathematical toolkit that enabled them to reshape continents. Deep within the dark, silent chambers of Europe's oldest caves, the evidence of this mathematical mind is painted on the walls in ochre and charcoal. We have long marveled at the stunningly lifelike depictions of bison, horses, and mammoths, seeing them as the purest expressions of early art. But look closer past the grand animals, and you will see another story told in dots, lines, and cryptic grids. These are not random decorations. They are a code, a numerical language that transformed the cave from a gallery into a sophisticated data repository. A horse is not just a horse, it is part of a sequence. A cluster of dots is not merely a background pattern, it is a tally. Researchers analyzing these symbols made a stunning breakthrough. They discovered that many of the dot clusters and notched lines correspond perfectly to the days in a lunar cycle. A set of 29 marks next to a pregnant animal might record a full lunar month, a primitive but accurate calendar tracking the rhythms of gestation and migration. Another panel, with its animals arranged in groups of 13 or 14, could be counting the days between key phases of the moon. This was a society using abstract symbols to quantify time itself, to predict the movements of the herds they depended on for survival. The mathematical thinking extends into the very composition of the art. The placement of the animals often follows strict proportional relationships. The distance from a bull's head to its tail, the space between two facing deer, these intervals are not accidental. They reveal a conscious use of spatial harmony, a geometric sensibility that guided the artist's hand as surely as it guided the builder's rope. What does this mean for our understanding of human intelligence? It tells us that mathematics was never a later invention. It was there from the very beginning, woven into the first stories we ever told. The drive to count, to measure, to find pattern was as fundamental to the human spirit as the drive to create beauty. In the flickering firelight of those ancient caves, art and mathematics were born as twins, two sides of the same profound impulse to make sense of a vast and mysterious world. This same drive to encode mathematics into the earth flourished independently across the ocean. In the river valleys of North America, Native American cultures engineered landscapes of breathtaking geometric scale. The Great Serpent Mound in Ohio uncoils across the land, a 1,300-foot-long effigy of a serpent swallowing a cosmic egg. Its curves are not freehand but precise mathematical arcs. The serpent's body aligns with the setting sun on the summer solstice, while the head and egg point to the rising sun of the winter solstice. This was a celestial clockwork carved into the soil, a massive calculation of solar cycles. But this was just one creation in a continent-wide tradition. The Hopewell and Mississippian peoples built vast ceremonial complexes composed of perfect geometric forms. They constructed enormous earthwork enclosures in the shapes of flawless circles, precise squares, and complex octagons, all connected by wide, straight causeways. To lay out a perfect square covering dozens of acres requires more than just a good eye. It demands advanced surveying. The builders used a consistent unit of measurement, now known as the Hopewell Standard Unit, a length of just over 1,000 feet that they applied across the entire Ohio Valley. This allowed separate communities, working over centuries, to contribute to a unified mathematical design. They understood how to create right angles using simple ropes knotted in the classic 3-4-5 Pythagorean ratio, ensuring their squares and octagons were perfectly proportioned. The true genius of these earthworks only becomes clear from an aerial view, a perspective the builders themselves never had. They were working from a master plan held entirely in their collective mind, translating abstract geometric ideals onto a colossal canvas of earth and grass. These were not just burial mounds or fortifications, they were mathematical diagrams of cosmic order, a testament to a sophisticated numerical science that emerged entirely on its own, rewriting the story of human discovery once again. High on a barren ridge in coastal Peru, a line of 13 stone towers stands as a silent, stone-cut computer. This is Chankillo, the Western Hemisphere's oldest known solar observatory, a masterpiece of astronomical mathematics carved into the desert landscape. These towers are not a fortress or a temple in the traditional sense. They are the meticulously calibrated teeth of a giant stone gear, designed to mesh perfectly with the movements of the sun. From two specific observation points, one to the east and one to the west, the entire solar year unfolds with breathtaking precision. On the December solstice, the sun would rise directly to the right of the first tower. Day by day, its rising point would shift, appearing in the gap between the first and second tower, then directly over the second. This celestial dance would continue throughout the year, with the sunrise position marching down the line of towers until it reached the far left at the June solstice, only to turn and march back again. The builders did not just note the solstices, they captured every single day of the solar year, transforming an abstract calendar into a physical, observable event. This required a profound understanding of solar geometry. They had to calculate the exact angle of the sun's path as it shifted north and south over the seasons, then translate that arc into a straight line of structures spaced at precise intervals. It was a work of astronomical triangulation, using the towers as fixed markers against the moving backdrop of the sky. The consistent height and spacing of the towers were not arbitrary. They were the result of complex calculations in angular measurement. The builders understood that the sun does not just move, it moves in a predictable mathematical pattern, and they engineered a way to read that pattern directly from the horizon. This was a society that had mastered calendrical mathematics. They could divide the year with astonishing accuracy, tracking the passage of time for agricultural, ceremonial, and social purposes. The entire structure is a testament to long-term data collection, the work of generations of observers who patiently recorded the sun's journey to create this permanent public timekeeping device. Chankillo stands alone, a unique and brilliant invention that proves the drive to quantify the cosmos was a universal human spark, igniting independently in the Americas just as it had across the Atlantic. That same mathematical intelligence was not reserved for monuments and earthworks alone. It lived in the hands of everyday people, etched into the clay of their pots and carved into the tools of their daily lives. Prehistoric pottery is far more than just functional container. It is a canvas of complex geometry. A simple bowl from an ancient village might seem unremarkable, but look at the pattern painted around its rim. You will often see a repeating design of diamonds, triangles, or zigzags. This is not random decoration. The perfect repetition, the unbroken symmetry, reveals a mind that has internalized the principles of measurement and proportion. To paint such a pattern, the artisan had to first mentally divide the circumference of the pot into equal segments. They were performing a fundamental geometric operation, calculating the division of a circle long before the concept of 360 degrees ever existed. The tools they used to create these patterns are equally telling. Bone combs used to stamp designs into wet clay often have teeth spaced with perfect regularity. These are, in effect, primitive measuring sticks, physical embodiments of a standardized unit of length. When we find the same precise spacing on pottery from villages hundreds of miles apart, it points to a shared mathematical language, a common understanding of measurement that facilitated trade and cultural exchange. The geometry deepens with the most beautiful artifacts. We find intricate spirals carved into stone pendants and bone jewelry. Many of these spirals are not just simple curls, they are logarithmic, their curves expanding at a constant geometric rate. This is the Fibonacci sequence made visible, the same pattern found in the seed head of a sunflower. To reproduce this in a small piece of amber or shale required more than a steady hand. It demanded a pre-planned design, a mental model of a complex growth pattern. The same is true for the breathtaking tessellations found on some artifacts, where interlocking shapes fit together without gaps or overlaps, like a prehistoric jigsaw puzzle. Creating a perfect tessellation requires an intuitive grasp of area, symmetry, and the properties of shapes, a form of recreational mathematics practiced thousands of years before it was formalized. Why does this matter? A massive stone circle is awe-inspiring, but it represents a communal, extraordinary effort. A perfectly painted pot, however, speaks to the mathematical mind of the individual. It shows that this knowledge was not the secret domain of a priestly class. It was a common, practical skill. The farmer who shaped a pot, the weaver who set up a loom, the carpenter who fashioned a joint, all were applying the same geometric principles used to build the great circles. They were all thinking in ratios and symmetries. This widespread, ingrained understanding of mathematics suggests a fundamental truth that the human brain is hardwired to seek out and create order. The patterns on a 5,000-year-old vase are not just decoration. They are the signature of a cognitive revolution, proof that the language of the universe was being spoken in every home, long before a single word of it was ever written. This mathematical genius becomes undeniable when we examine the sheer physics of these monuments. Think of the multi-ton stones at Stonehenge or the colossal pillars of Göbekli Tepe. Moving a 25-ton block of sarsen stone over 20 miles of rolling countryside was not a matter of brute force. It was a complex logistical equation. The builders had to calculate the force required, the number of people or animals needed to pull the load, and the most efficient path. They likely used a system of sledges, rollers, and levers, which demanded a practical, working knowledge of mechanics. They understood how to reduce friction, how to distribute weight evenly, and how to use leverage to tilt and raise stones that weighed as much as a modern bus. This is applied mathematics in its purest form, the calculation of force, mass, and motion to solve a real-world problem. The placement of these stones reveals an even deeper layer of engineering mathematics. Before a single stone was set upright, the builders had to prepare the foundation. At many sites, the stone sockets were dug with sloping sides to cradle the base of the monolith, a deliberate design that increased stability. They were thinking about the center of gravity, calculating how to anchor these towering masses against wind and weather for thousands of years. The famous trilithons at Stonehenge, with their massive lintels perched atop two vertical stones, are a masterclass in load distribution. The weight of the horizontal stone is transferred perfectly down through the uprights and into the earth. This is not guesswork. It is the result of an intuitive yet highly accurate understanding of structural physics. They knew that for the structure to stand the test of time, every force had to be channeled and balanced according to an unseeable mathematical law, but the true precision is found in the joins. At sites across the world, from Malta to Scotland, we find stones that fit together with a seamlessness that defies their age. They did not use mortar. Instead, they shaped the rock itself. Using only stone hammers and abrasives, they carved intricate joints directly into the granite or limestone. The most famous are the mortise and tenon joints, where a protruding knob on one stone fits perfectly into a carved hollow on another. Others used complex tongue and groove systems, interlocking the stones like a three-dimensional puzzle. To achieve this, the builders required a sophisticated knowledge of geometry and measurement. They had to visualize the final form in 3 dimensions, then calculate the exact angles and depths needed for a perfect fit. This is stereotomy, the art of stone cutting, a skill we associate with classical architects, yet here it is being practiced millennia earlier. The architectural designs themselves are mathematical models for stability. The corbelled roofs of Newgrange and other passage tombs are a perfect example. Each layer of stone is set slightly inward from the one below, cantilevering over the empty space until the vault is closed at the top. This creates a self-supporting arch that redirects the immense weight of the earth mound outwards and downwards, away from the open chamber below. The builders calculated the precise angle of inward slope needed to achieve this balance, a calculation that has kept these chambers dry and intact for over 5,000 years. How did they acquire this knowledge without formal training or written formulas? It was a tradition passed down through generations of master builders, a living library of mathematical and engineering principles refined through trial, observation, and an intimate understanding of material properties. They learned which stones could bear the most weight, how to shape them for strength, and how to assemble them into a unified, stable whole. These monuments were not just spiritual centers, they were the ultimate tests of a society's collective mathematical intelligence, projects that demanded the precise application of geometry, physics, and mechanical engineering on a scale that still inspires awe and bafflement today. The same mathematical principles that raised megaliths were also painted onto canyon walls and cave ceilings. Scattered across the globe, ancient rock art galleries hold a secret. They are celestial maps rendered in ochre and charcoal. Look past the majestic elk and charging bison, and you will see a sky chart. A cluster of dots is not random. It is the Pleiades star cluster. A series of parallel lines does not just frame a scene, it counts the nights between lunar phases. This is mathematics translated into a visual language, a code for tracking time by the stars. The artists were astronomers, meticulously recording the slow dance of the cosmos on their rocky canvases. In North America, a petroglyph of a spiral might be positioned so that a dagger of sunlight pierces its center only on the day of the summer solstice. In Scandinavia, a carving of a ship could be oriented to point toward the winter solstice sunset. These alignments are not coincidental. They required generations of patient observation, of noting the exact position of the sun on the horizon each day, year after year, until a pattern emerged. That pattern was then encoded into the very placement of the art. To achieve this, the artists needed a sophisticated understanding of angles and sightlines. They were effectively turning the entire landscape into a giant protractor, using natural features and their own carvings as fixed points to measure the sky's movements. Some sites functioned as complete observatories. A single, strategically placed petroglyph could act as a foresight, lining up with a distant mountain notch to mark the equinox. The entire panel becomes a permanent calendar, a stone-cut almanac that predicted the changing seasons for the community. This was a global phenomenon. From the sun-worshipping cultures of the American Southwest to the hunter-gatherers of the Australian outback, we find the same impulse to marry art with celestial mathematics. They did not need telescopes or written tables. They had sharp eyes, patient minds, and the drive to find order in the heavens, a drive that led them to independently discover the same mathematical truths about our universe. The greatest monuments our ancestors built were not always made of stone. Some were the voyages themselves, epic journeys across trackless oceans that required a mathematical mind of the highest order. Long before the compass or the sextant, prehistoric seafarers were navigating the open sea with a sophistication we are only beginning to understand. Their vessel was not just a hollowed-out log, but a platform for a complex science of observation and calculation. To cross hundreds of miles of open water, they had to become living computers, processing a constant stream of environmental data. They learned to read the stars not as static pictures, but as a moving clockwork. The Polynesians, for instance, mastered the art of wayfinding by memorizing the precise rising and setting points of hundreds of stars. They understood that each star was a fixed point on a celestial sphere, and by knowing which one passed directly overhead, they could determine their latitude. This is a practical application of spherical geometry, mapping the curved dome of the sky onto the flat plane of the ocean, but the stars were only part of the equation. During the day, they watched the sun, noting its arc and using its position to maintain a steady course. They observed the subtle patterns of ocean swells, how certain wave trains reflected off distant islands, creating an interference pattern that could be felt miles out to sea. They became experts in reading the flight paths of birds. A particular species flying out at dawn and returning at dusk indicated land was near, and its direction was a living compass. This was not random guesswork. It was a mathematical modeling of nature. They were integrating multiple variables, star positions, wave direction, bird behavior, into a single, coherent mental map. This required an innate grasp of probability and vector analysis, constantly updating their estimated position based on new observations. The success of these voyages, populating remote islands across the Pacific, stands as irrefutable proof of this applied mathematics. It challenges the comfortable idea that math was invented for counting grain or measuring fields. Here, mathematics was a tool for pure exploration, a lifeline that enabled humanity to conquer the final frontier of its age, the sea. It reveals a mind that could not only build circles of stone on land, but could also use the geometry of the cosmos to navigate the infinite blue. These prehistoric calendars were the operating systems of their entire world. They were not just marking days, they were modeling time itself, using mathematical principles to predict the future with stunning accuracy. The solstice alignment of a single stone is impressive, but a full calendar requires tracking multiple overlapping cycles. The sun gives us the year, the moon gives us the month, and these cycles do not fit together neatly. A lunar month is about 29.5 days, while a solar year is roughly 365.25 days. Prehistoric calendar makers had to reconcile these incompatible periods, a mathematical puzzle that required finding a common multiple. This is where their computational genius truly shines. We see evidence of lunisolar calendars, complex systems that interlock the lunar and solar cycles. They discovered that a certain number of lunar months almost exactly equals a whole number of solar years. The most famous of these is the 19-year Metonic cycle, where 235 lunar months equal 19 solar years with an error of just a few hours. Astonishingly, this same cycle appears to be encoded in the geometry of Stonehenge, suggesting its builders had identified this complex periodicity thousands of years before the Greek astronomer Meton gave it his name. This was not simple counting. This was long division and multiplication on a grand temporal scale. They were thinking in terms of least common multiples and harmonic intervals, breaking down the chaotic flow of time into predictable mathematical units. These calendars allowed them to see years, even decades, into the future. They could predict an eclipse not as a terrifying omen, but as a predictable celestial event, a function of the moon's orbit. They could announce the precise day for planting seeds weeks in advance, coordinating the labor of an entire society. This mathematical foresight transformed human civilization from a species that simply reacted to its environment into one that could plan, predict, and profoundly shape its own destiny. This mathematical blueprint for society did not stop at temples and tombs. It laid the very foundations of the first cities. Long before the rise of empires, prehistoric urban planners were designing entire communities with a geometric precision that rivals modern engineering. The ancient city of Çatalhöyük, a sprawling settlement in Anatolia dating back over 9,000 years, presents a stunning example. Its labyrinth of homes was not a chaotic jumble. The entire city was a dense, interconnected hive, with buildings packed so tightly that residents moved across the rooftops, using ladders to descend into their homes. This was not random growth, it was a master plan executed in mud brick. The structures were almost perfectly rectangular, their walls parallel and aligned on a consistent orientation. This uniform layout required a shared understanding of right angles and linear measurement, a common geometric language that every builder in the community understood and followed. The streets, or rather the organized spaces between structures, followed deliberate pathways that facilitated movement and social interaction, demonstrating a conscious application of spatial mathematics to manage human traffic and community life. This geometric order extended far beyond the architecture itself, into the very systems that kept the city alive. The builders engineered a sophisticated water management scheme. They constructed clay pipes and drainage channels with precise, calculated gradients. Getting the slope right was a matter of mathematical necessity. Too steep and the water would rush away too quickly, eroding the channels; too shallow and it would stagnate. They had to perform constant hydraulic calculations to ensure a steady, controlled flow for sanitation and fresh water. This was civil engineering on a grand, urban scale. Even the placement of ovens and hearths within the homes shows this mathematical thinking, positioned for optimal heat distribution and ventilation according to principles of airflow and thermodynamics they could not name but understood perfectly. These were not just collections of houses, they were mathematically modeled ecosystems, where every building, every channel, and every pathway was part of a single, cohesive design for sustainable living. The very existence of such planned settlements reveals that mathematics was the invisible framework holding the first complex societies together, the essential tool for turning a village into a city. Even in death, the ancient mind was governed by numbers. Prehistoric burial sites are far more than resting places for the departed. They are complex mathematical diagrams etched into the earth. From the grand passage tombs to the simplest grave mounds, the architecture of the afterlife reveals a sophisticated understanding of geometry, astronomy, and structural physics. The very first decision in creating a tomb was its orientation, and this was almost never left to chance. Grave entrances and chambers were meticulously aligned with celestial bodies, most commonly the rising or setting sun on a solstice or equinox. This was not a vague directional preference, it was an act of precise angular measurement. To capture the first ray of the midwinter sun, as seen at Newgrange, required calculating the exact azimuth, the horizontal angle, of the sun's position on the horizon. This is spherical trigonometry applied to a spiritual purpose, connecting the journey of the soul with the immutable mathematics of the cosmos. Inside the tomb, the geometry deepens. The layout of burial chambers frequently follows strict proportional relationships. The length of a passageway might relate to the width of the chamber by the golden ratio, creating a space that feels inherently harmonious. In other sites, the chambers are arranged in cruciform or cloverleaf patterns, their intersecting axes forming perfect right angles and symmetrical divisions of space. This is sacred geometry, the belief that certain mathematical forms and ratios hold profound power, used to create a bridge between the physical world and the realm of the spirits. The construction of these tombs was a masterclass in structural mathematics. The corbelled roofs we find in passage tombs across Europe are a perfect example of this. Each stone layer is set slightly inward from the one below, cantilevering over the empty space until the vault is sealed at the top. This design creates a self-supporting arch that redirects the immense weight of the earth mound outwards and downwards away from the sacred chamber. The builders had to calculate the precise angle of this inward slope, a mathematical balance that has kept these spaces intact for over 5,000 years. They understood load distribution intuitively, knowing exactly how to stack and shape stones to withstand colossal pressure. What is truly astonishing is the consistency of these mathematical principles. From the stone-lined cists of Scandinavia to the megalithic tombs of the Mediterranean, the same patterns emerge: astronomical alignments, geometric proportions, and stable vaulting techniques. This was not a single culture's secret. It was a universal expression of the human mind. In facing the great mystery of death, cultures across the globe and across millennia independently turned to the same language, the language of mathematics, to build a permanent, ordered sanctuary for their ancestors. The tomb was a physical equation, a final statement that even in our end, we are part of a grand, predictable, and beautiful cosmic order. Deep beneath the surface, our ancestors were solving complex engineering problems in the dark. The prehistoric mines at sites like Grimes Graves in England or the massive flint quarries of continental Europe were not simple holes in the ground. They were carefully planned subterranean projects that demanded a sophisticated grasp of geometry from the very first strike. Before digging, miners had to calculate the most stable shape for their shafts and tunnels to prevent catastrophic collapse. They consistently chose specific angles for their walls and developed pillar and room systems, leaving behind sturdy columns of untouched rock to support the immense weight overhead. This was a practical application of load-bearing mathematics, an intuitive understanding of how forces distribute through the Earth. The precise, repetitive angles and symmetrical layouts found in these ancient networks reveal a mind that was thinking in three-dimensional geometric models long before such concepts had formal names. The true mathematical challenge, however, began once the precious flint or ore was loosened from the Earth. How do you move tons of rock from the bottom of a deep, narrow shaft? The solution was a feat of mechanical engineering. They constructed complex ramp systems, calculating the optimal incline to minimize the effort needed to haul baskets of material to the surface. This required an innate understanding of the mathematics of inclined planes, effectively reducing the force required by strategically increasing the distance. The organization of the labor itself was a masterpiece of logistics. A single mining operation involved teams of diggers, haulers, toolmakers, and surface processors, all working in a coordinated rhythm. This was not chaotic activity. It was a system governed by mathematical principles of resource allocation and workflow efficiency. The miners had to calculate how much raw material was available, how many workers were needed to extract it, and how to sustain the operation over weeks or months. They were effectively running a prehistoric corporation, relying on a shared, unspoken mathematical model to manage supply chains, labor hours, and output long before the invention of management science. These dark, silent tunnels prove that mathematics was not confined to temples and calendars. It was the essential, practical intelligence that fueled humanity's first technological revolutions, hidden from the sun but brilliant in its execution. This same mathematical intelligence flowed into the very lifeblood of early civilization, water. Beyond the sacred circles and celestial tombs, prehistoric societies were engineering landscapes on a hydraulic scale, building canals, reservoirs, and irrigation networks that transformed arid lands into fertile breadbaskets. The construction of these systems was a monumental exercise in applied mathematics, demanding a sophisticated grasp of volume, flow, and gradient. To divert a river into a canal, engineers first had to calculate the volume of water needed to nourish distant fields. This was not a guess, it was a careful estimation of capacity, a balancing act between supply and demand that determined the width and depth of each channel. The true genius, however, lay in controlling the water's movement. They understood that water only flows downhill, and they mastered the mathematics of slope. Creating the perfect gradient was critical, a precise calculation of rise over run. If the channel was too steep, the water would rush through, eroding the walls and carrying away precious topsoil. If it was too shallow, the water would stagnate, clogging the canals with silt and never reaching the fields. Getting this right required constant surveying, using simple tools like sighting poles and weighted cords to maintain a consistent, gentle drop across miles of terrain. This was practical calculus in action, a continuous calculation of rate and change executed with rope and stakes. The geometry of these networks is equally impressive. Canals were laid out in straight lines and gentle curves, their alignments following the most efficient path across the landscape. This required geometric planning to navigate around hills and across gullies, often involving the construction of aqueducts or underground tunnels. The channels themselves were shaped using specific ratios, their cross-sections designed to maximize flow while minimizing erosion. At the heart of these vast projects was a profound understanding of structural stability. The walls of reservoirs and the embankments of canals were engineered with specific angles of repose, the same mathematical principle that kept Silbury Hill standing. They knew exactly how to slope an earthen dam to withstand the immense pressure of thousands of gallons of water. The scale of coordination was staggering. Vast irrigation networks, like those found in early Mesopotamia or the Andes, required a centralized plan and a shared unit of measurement. Teams of workers digging separate segments of a canal miles apart had to follow the same master blueprint, ensuring that every channel would connect perfectly and water would flow seamlessly from its source to the most distant farm. This was mathematics governing survival. The ability to manage water mathematically directly fueled the agricultural surplus that allowed villages to grow into the world's first cities. It was a practical, earth-bound science that emerged independently in river valleys across the globe, from the Indus to the Yellow River, proving once again that the human mind will discover the same mathematical truths whenever the need is great enough. The fire of the forge was a crucible for mathematics as much as for metal. To transform raw rock into gleaming copper or bronze, prehistoric smiths had to become masters of an invisible numerical world, one governed by temperature, proportion, and chemical reaction. Their success was not a matter of luck, but of precise, calculated processes. The very first challenge was achieving the correct temperature. Different ores melt at different heats, and exceeding or failing to reach that critical point meant the difference between a useful metal and a worthless slag. These early metallurgists learned to gauge temperature through careful observation, correlating the color of the coals and the glow of the furnace interior with specific heat ranges. This was a practical, intuitive form of thermal mathematics, a calibration of fire itself. The design of their furnaces was a geometric puzzle. They built clay and stone structures with specific internal shapes and air channels to maximize heat retention and airflow. The placement of the tire, the pipe that delivered air from bellows, was calculated to create a perfect combustion zone, a feat of aerodynamic and thermal engineering. But the true mathematical genius emerged in the creation of alloys. A pure metal like copper is relatively soft, but mixing it with a precise amount of tin creates the far stronger bronze. The smiths discovered that the properties of the final metal depended on exact ratios. Too much tin and the alloy becomes brittle, too little and it remains soft. Through generations of experimentation, they arrived at the ideal proportional relationship, often around 9 parts copper to 1 part tin. This was chemistry guided by mathematics, a recipe for innovation that transformed societies. They were thinking in percentages and fractions long before those concepts had formal names, their crucibles serving as the laboratory where abstract ratios were forged into tangible progress. This was not abstract theory, it was mathematics in action, the essential, unspoken intelligence that powered humanity's first great technological leap. The true scale of this mathematical mind becomes clear not in its monuments, but in its markets. Vast prehistoric trade networks, stretching from the shores of the Mediterranean to the forests of northern Europe, functioned as a silent, continent-wide school of mathematics. For trade to work over such immense distances, a universal language was needed, and that language was numbers. The first challenge was establishing trust between people who had never met, who spoke different tongues and worshipped different gods. The solution was a system of standardized weights. Archaeologists find remarkably consistent stone weights across these ancient routes, little carved cubes and spheres that represented a fixed unit of mass. A merchant in Anatolia could place a specific weight of copper on one side of a simple balance scale, and a trader from Mesopotamia could add lapis lazuli to the other until it balanced. Both knew the exchange was fair, not because of a shared language, but because of a shared mathematical standard. This required an incredible conceptual leap, the idea that an abstract value could be consistently represented by a physical object, a concept that is the very foundation of currency. These weights were not rough approximations. They were precision-made, often following a strict binary or decimal system, where a large weight was exactly 2 or 4 or 10 times heavier than a smaller one. This is multiplicative thinking, a sophisticated understanding of proportional relationships that allowed for complex calculations of value. Imagine a trader calculating how many bags of grain were equal to a single amber pendant, using nothing but a set of standardized stones and a mental grasp of ratios. This was mathematics as the engine of commerce, a practical tool that enabled the first globalized economy. But the mathematics of trade went far beyond the marketplace. Organizing the routes themselves was a feat of logistical modeling. Caravans and ships did not wander aimlessly. Their journeys were planned using a mathematical understanding of distance and time. They knew that a journey of 100 miles on foot would take approximately 10 days, accounting for terrain and rest. This is a primitive form of the distance-rate-time equation, a fundamental algebraic relationship. They had to calculate the carrying capacity of a ship or a pack animal, balancing the weight of trade goods against the supplies needed for the voyage. This was an optimization problem, maximizing profit while ensuring survival. The development of early accounting was the final, crucial piece. Before writing could record poetry or laws, it was used to track numbers. The earliest clay tablets from Mesopotamia are not literature, they are inventories and receipts. We see the same impulse in prehistoric Europe, with notched tally sticks and marked clay tokens that recorded debts, quantities of goods, and complex transactions. This was the birth of data management. A village elder might have a stick with a series of carved lines, each one representing a jar of oil owed to a distant trader. This system required abstract numerical thinking, the ability to let a physical mark stand for a quantity and to keep a running total. These networks were not just exchanging goods, they were exchanging ideas, and the most important idea they spread was a mathematical one, the concept that the world could be measured, valued, and understood through numbers. This was not abstract theory conceived in a temple. It was mathematics born from the dusty, practical necessity of a fair deal, proving that the roots of our global economy are not in gold, but in geometry. The same mathematical mind that calculated celestial cycles was also finely tuned to the physics of sound. Deep within ancient caves and burial sites, we have uncovered musical instruments of astonishing complexity, flutes carved from the wing bones of birds and mammoth ivory. These are not crude noisemakers. They are precision-engineered devices that prove our ancestors understood the mathematics of harmony thousands of years before the first written note. The creation of a simple flute was an exercise in applied acoustics. The instrument maker had to calculate the exact length of the air column to produce a specific fundamental tone. A longer bone produced a deeper, lower note, while a shorter one created a higher pitch. This is a direct physical manifestation of a mathematical relationship, the inverse correlation between length and frequency. But the true genius lies in the placement of the finger holes. To create a scale, the holes could not be spaced arbitrarily. their positions along the tube had to correspond to precise fractions of the total length. A hole placed exactly halfway down the flute's body would produce a note 1 octave above the fundamental tone. Other intervals, like the perfect fifth or the fourth, were created by placing holes at the 2/3 or 3/4 point. These are the pure, simple ratios that form the foundation of all Western music, the same ratios the Greek philosopher Pythagoras would later discover using a monochord. The builders of these flutes were not just musicians, they were acoustic engineers using proportional mathematics to map the harmonic series directly onto a physical object. The consistency is what is truly staggering. Flutes found in different parts of the world, carved by cultures with no contact, often use the same mathematical intervals. This suggests that the human ear, and by extension the human mind, is naturally wired to find beauty in these specific numerical relationships. The drive to create music was, in essence, a drive to discover the mathematical order hidden within sound itself. This knowledge was not limited to melody. The construction of early drums and stringed instruments reveals a similar grasp of acoustic principles. The size and tension of a drumhead had to be carefully calibrated to produce the desired resonance and pitch. A drum that was too taut would sound sharp and brittle, while one too loose would produce a dull thud. The makers had to intuitively understand the relationship between surface area, tension, and the resulting frequency, a complex equation of vibrations. This mathematical sophistication transforms our understanding of prehistoric life. It reveals a world not of brute survival, but of profound cultural richness, where the same brain that could chart the stars and raise megaliths could also calculate the precise position of a hole to bring a haunting melody to life. Music and mathematics were not separate disciplines. They were two expressions of the same fundamental human impulse to find pattern, proportion, and beauty in the universe. The same mathematical genius that raised stone circles was woven into the very fabric of prehistoric life, quite literally. Long before the loom was a common household object, the creation of textiles was a silent, intricate exercise in applied geometry. Every piece of cloth began not with thread, but with a mental blueprint, a complex pattern held in the weaver's mind. To create a simple checkerboard design, the artisan had to calculate the precise sequence of over and under, a binary code of zeros and ones executed with fiber. More complex twills and diamond patterns required planning multiple sequences of threads, predicting how each row would interact with the one below it to form a cohesive, repeating whole. This was mathematics made tangible, a fabric of interlocking ratios and symmetries. The very structure of the loom itself was a geometric grid, a physical coordinate system where the vertical warp threads and the horizontal weft created a living matrix. The weaver had to understand the proportional relationship between warp tension and weft density, calculating how tightly to pack the rows to achieve a cloth that was neither too stiff nor too loose. This was a constant, hands-on calculation of density and spacing, a practical science of material properties. The patterns they created were not random. We find the same precise spirals, zigzags, and fractal-like motifs in textiles that we see carved into megalithic tombs. A woven band might display a perfect Fibonacci sequence, its expanding curves a visual echo of a nautilus shell. To replicate this pattern required the weaver to increment the count of threads in each row according to a strict, predetermined numerical rule. This is algorithmic thinking, a step-by-step computational process used to create beauty. The mathematics extended beyond the loom into the dye pots. Creating a consistent, vibrant color was a problem of chemistry and ratio. To achieve a specific shade of red from madder root or blue from woad, the dyer had to mix plant extracts and mordants in exact proportional relationships. Too much alum and the color might turn muddy, too little and it would wash out. They were working with recipes that were, in essence, chemical formulas, balancing quantities to trigger the desired reaction between fiber and dye. This knowledge was not haphazard. The discovery of standardized textile sizes and identical pattern motifs across vast distances tells a story of shared mathematical concepts. A cloth woven in one village would fit a garment made in another because both cultures used the same underlying unit of measurement, a textile cubit passed down through generations. This unspoken numerical language allowed for trade, cultural exchange, and the preservation of complex technical knowledge without a single written manual. The humble textile, often seen as a domestic craft, was in reality a testament to a widespread, ingrained mathematical intelligence. It proves that the logic of numbers and patterns was not confined to monuments, but was a living, breathing part of daily existence, woven into the very clothes our ancestors wore. This same mathematical intelligence was not reserved for monuments and trade. It was the bedrock of survival itself, cultivated in the very soil. The shift from hunting and gathering to farming was not just a change in diet, it was a revolution in applied mathematics. To feed a growing population, our ancestors had to become land managers, hydraulic engineers, and statisticians, all without a single textbook. The first and most visible application was in the geometry of the fields themselves. Early farmers did not simply scatter seeds randomly. They laid out their plots with deliberate geometric precision. Fields were often divided into long, rectangular strips or perfect squares, a design that maximized the use of available land and simplified the process of tilling and planting. This required a shared understanding of area and perimeter, using simple ropes knotted at regular intervals to measure out equal plots for different families or clans. The very shape of agriculture was a mathematical decision, an optimization problem solved with stakes and cord, but the geometry went deeper than simple plots. In some regions, we find evidence of contour plowing, where furrows were cut in curves that followed the natural shape of the hillside. This was not an aesthetic choice. It was a calculated method to prevent soil erosion, a practical application of topographic mathematics that understood how water flows across a slope. They were modeling the land in 3 dimensions, using geometry to protect their most vital resource. The true mathematical challenge, however, was water. An irrigation channel is a river of calculations. To bring water from a source to a distant field, farmers had to become masters of flow and volume. They first had to calculate how much water their crops would need, a rough estimation of consumption that determined the capacity of their canals. Then came the precise engineering of the channels themselves. The gradient was everything. Using sighting poles and water levels, they surveyed the land to create a constant, gentle slope. If the channel was too steep, the water would rush through and erode the earthen walls. If it was too shallow, the water would stagnate, depositing silt and never reaching the thirsty plants at the end of the line. This was a continuous exercise in applied calculus, a careful balancing of rate and distance executed across the landscape. The distribution of water was another layer of mathematical planning. Complex networks of smaller channels branched off from the main canal, delivering measured amounts to different fields. This required a system of gates and weirs, mechanisms that allowed for the controlled division of the flow. Managing this fairly among an entire community demanded a shared understanding of fractions and proportional division, ensuring that every farmer received their rightful share of the life-giving resource. This mathematical foresight extended from the field to the granary. Storing the harvest was a problem of volume and prediction. builders constructed silos and pits with specific capacities, calculating how much grain was needed to sustain the population through the lean winter months. They had to model future need, estimating consumption rates based on the number of people and the length of the off-season. This was an early form of statistical modeling, a projection that balanced current abundance against future scarcity. The entire agricultural cycle was governed by a celestial clock. The development of precise agricultural calendars was perhaps their most sophisticated mathematical achievement. Planting and harvesting are not fixed dates on a modern calendar, they are events tied to the sun's position. By tracking the solstices and equinoxes and noting the heliacal rising of certain stars, these early farmers could predict the coming of the rains and the exact window for sowing seeds. This was not passive observation, it was active, long-term data collection. They were identifying patterns in the chaos of weather, correlating celestial events with terrestrial outcomes. This allowed them to plan not just for the next season, but for generations, creating a stable, predictable food supply that became the engine of civilization. The field, the canal, and the granary were their laboratories, and mathematics was the silent, essential language that allowed humanity to finally master its own sustenance. These silent stones form a coherent argument, a global testimony written in geometry and aligned with the stars. Our journey through these ancient sites reveals a startling and inescapable truth. Advanced mathematical thinking was not an invention of early civilizations, but a fundamental capacity of the human mind, flourishing long before the first word was ever written. From the geometric precision of Göbekli Tepe to the celestial calendars of Chankillo, our ancestors demonstrated a sophisticated grasp of mathematical principles. They manipulated abstract concepts of ratio, angle, and proportion. They modeled the cosmos and engineered structures that have endured for millennia. This evidence does not simply add a footnote to history. It challenges the very timeline of human intellectual development. We have long told a story of a linear progression from primitive hunter-gatherer to literate, civilized farmer. But these stone blueprints tell a different story, one of a cognitive Big Bang that occurred in the human mind thousands of years earlier than we ever suspected. Mathematical cognition appears to be a core component of human intelligence, a universal language that cultures across the globe discovered independently whenever the need arose, whether for building, farming, trading, or understanding the heavens. This is not about finding a lost super-civilization. It is about recognizing the profound genius inherent in our own species. The capacity for abstract mathematical thought was there all along, woven into the fabric of our consciousness. As we continue to decode these stone blueprints with new technologies and fresh perspectives, we are not just learning about ancient engineering, we are gaining profound insights into the capabilities of the prehistoric mind. We are learning that the drive to find order, to quantify, and to measure is a defining human trait. The stones have been speaking to us for millennia in a language of lines, angles, and celestial alignments. We are only now, finally, learning how to live.